Okay, guys, in the previous video we talked about intramolecular bonding in terms of ionic bonding, making up ionic compounds. Now it's time to talk about a different type of intramolecular bonding within chemical compounds, and we're going to talk about metallic bonding. This is a type of bonding that occurs only between metals and metals. Either of the same type, then we have a pure element, or between different types of metals when we have, for example, alloys of various types. On this picture, I have drawn two metals, two Chadwick models of lithium, and we can see that due to the presence of 3 protons in each, remember, 3 protons defines which element we have, and we have 4 neutrons, which symbolizes lithium-4, which is the most common isotope of lithium. But there are others, of course. Right. If we're talking about electronegativity, well, if we have a lump of metal that only contains one element, then the difference in electronegativity is going to be 0. If we talk about alloys, it's not going to be 0 in difference in electronegativity, but it's going to be rather low. In metallic bonding, metal atoms share valence electrons with each other. And these valence electrons can move within the metal crystal. Right. So, remember that metals have a low value of electronegativity, therefore they do not attract their outermost electrons very hard, the valence electrons. And what happens in a metal when several metal atoms come together is that they're pretty much losing hold of their valence electron, like so, and form positive cations. Of course, when we talk about a larger metal crystal, we have much, like way more atoms that are shown here. We only have 2. We're talking about billions and billions of atoms. So it's rather hard to model this with individual electrons when we talk about larger structures. Therefore, we usually model metals this way, metal crystals this way, that we have individual metal cations within it, and then a shared electron cloud. So shared means that these metals will share all of these electrons. So at a given point of time, an individual cation, like this lithium cation here, is going to be attracted to a specific electron, but this electron moves and the attraction is going to be to another one, and so on. And this is our model of a metal crystal. It's cations surrounded by a shared electron cloud. So what's the actual bonding then? Well, all types of chemical bonding involves electrostatic attractions between plus and minus, like we talked about. In this case, electrostatic interactions between protons and neutrons. And the type of bond that's formed within metals is just an electrostatic attraction between the electrons in the electron cloud and the cations. So they stick together. And since several cations are pulling on a shared electron cloud, they stick together. And this is called metallic bonding, which we see in metal crystals. So let's look at a lump of iron, which I have a picture of here from Wikipedia Commons. It's an iron crystal, as I'm referring to it, and we'll get into what I mean with a crystal structure. But it's a lump of iron, all right? And based on the source behind this picture, this piece corresponds to 16 grams of iron. Not that much. If we calculate this and convert this to the number of atoms within this lump of iron, this iron crystal, It corresponds to this number written here, which is a very, very large number, to be fair. And that's going to be really hard when we're going to write up a chemical formula involving iron. We don't write up all of these individual atoms. What we do instead is we write the empirical formula. And the empirical formula shows the smallest ratio between elements or components in the compound. So the smallest ratio between what type of components we have. In this case, this crystal is only built up from one component, and that's iron atoms. So the lowest ratio between iron atoms is, it's just a small repeating unit, and that's an iron atom. So whenever we write an empirical formula, when we write a metal involved in some sort of chemical reaction, we write the lowest repeating unit, smallest repeating unit, and that's an individual iron atom. But of course, this is an empirical formula, and usually we have lots of iron atoms. Look at this number, which is huge. Lots of iron atoms that stick together via metallic bonding. But when we write chemical formulae, we only write an individual atom like this if we have just one element within our metal crystal. Bit different if we have a alloy of some sort. We talked about the properties of ionic compounds. Let's look at the properties of metallic compounds or metals. Because the metallic bonding is going to give some rather intriguing properties to metals. So, metals conduct electricity all the time, even when they're in a solid state. This in contrast to ionic compounds, which only conduct electricity when their ions are delocalized or moving. So for an ionic compound, we needed a liquid or a solution of that ionic compound. But metals, they conduct electricity all the time, also in a solid state. Another contrast to ionic compounds is that metals are malleable. That means that instead of breaking easily into smaller parts like a salt crystal, they rather bend if we subject them to force. Another thing that's usually taken up when we talk about metals and metallic properties is that metals have a metallic luster. They have a nice shine to them. So if you encounter some sort of powder and you zoom in on this using a microscope and you see some sort of metallic luster, it could be a metal you're looking at. Quite often in real life, we deal with alloys. That's homogeneous mixtures of various metals in various proportions. And remember, mixtures, the chemical properties are dependent on the amount of the components. So dependent on how much we have of each metal, we're going to have different chemical properties. Furthermore, various metals can have a different hardness or a different strength. Some metals are fairly easy to break or bend. It's fairly easy to bend, whereas other metals are going to be really hard to bend. And how do we explain this? Well, let's think about alkaline earth metals and compare them to alkali metals. The alkaline earth metals, remember, they donate 2 valence electrons, and within a metal they're going to donate 2 of their valence electrons to this shared electron cloud. Then we're going to have an interaction with a 2+ charge and way more electrons than we would have if we had alkali metals. When an alkali metal, for example sodium, donates its electron to a shared electron cloud, we have the interaction between a single plus charge and the electron cloud, which is also less electron dense. So the more electrons that are donated and the larger difference in charge, the stronger these interactions. So a larger value on these charges, the stronger interactions, and that translates to a harder metal. Let's try to explain using a simple model of a metal crystal why metals are malleable. Say that we subject this piece of metal to some violence. We hit it with a hammer. what's going to happen? Well, I mean, we're going to shift atoms. We're going to bend this metal if we hit it hard enough with our hammer. But in contrast to when we looked at the ionic compounds, where we got charges of anions of different type next to each other, in this case, the electron cloud shields the positive metal cations from each other, even when we shift the structure within the crystal. So this is what we're going to end up with, a bend or a groove in our metal that we just hit with a hammer, but it's not going to charges are not going to repel each other the same way as in a ionic compound. We're just going to end up with this sort of structure. Okay, so we've been comparing metals to ionic compounds. Let's do that in a bit more detail. So to the left, we're going to have lithium, how it behaves as a metal. And to the right, we're going to look at lithium as an ionic compound. Right? So as a metal, lithium is going to be in the shape of a metal crystal. When lithium has formed an ionic compound, it takes the shape of a salt crystal. In the salt crystal, we have interactions between cations and anions. In the metal crystal, we have interactions between cations and shared electrons, a shared electron cloud. This gives the metal its malleable property, that it can be bent. If we compare it to crystals, you remember that ionic compounds and their crystals, they are brittle and easily broken. So there's a difference there. Lithium as a metal conducts electricity all the time. As a salt, it only conducts electricity when it's liquid or dissolved. Furthermore, when lithium is as a metal, it reacts rather reactively with water, as we looked at before, because it's an alkali metal. And instead of sharing an electron cloud like this, it would prefer to form some sort of salt compound, some sort of ionic compound. So it's really reactive and reacts even with water, if we mix it with water. If we mix a lithium salt with water, it's not going to react with the water in a chemical reaction where electrons are moved. Rather, it's going to be dissolved, but it doesn't react in a chemical reaction. So here's three different things we're comparing. So we see that dependent on if we have lithium as a metal or as an ionic compound, we have vastly different chemical properties to deal with. And I've been talking quite a lot about crystals, both about crystals when we talk about ionic compounds and when we're talking about metals, which may seem strange to some of you because you usually don't think about metals as crystals. But if you look this up, the definition of a crystal is a specific microscopic pattern that is repeated over and over again in a regular arrangement in 3 dimensions, like, for example, our metal crystals. The cations are going to be ordered in a systematic manner, like this, with electrons between them, and this fulfills the criterion for being called a crystal. Same goes for the salt crystal of, for example, a lithium salt. We see a regularity of how it's changed. We see a microscopic pattern that's repeated over and over again. There are, of course, other types of crystals, not just metals and ionic compounds. We have, for example, this, which is a picture of a diamond. Diamonds are covalent compounds, molecules. Here we see a snowflake, a water crystal formed from a molecule of water in a solid state. So crystals can be pretty much anything, as long as we have a specific pattern that repeats over and over again in 3 dimensions. Next video is going to be about covalent bonding and how electrons interact with each other. But I think that will do for now.